Also, weil wie,
Hola, 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 buenos días. Buenos días.
hacia la pantalla principal. Es el cel. No, le doy un clic, pero no va.
The first
Sí,
day was
sí.
like,
La otra,
no, I'm fine.
hola, hola. Sí,
Sí. Sí.
buen día, sí. Dos.
Micrófono de ahí, la pantalla.
Estos
Micrófono del Zoom.
para ponerte quiénes son.
Ajá.
Hola, 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 hola. Hola, hola, sí, 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 mira, 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 mira. Sí, 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 sí. Ahora sí, 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 ahora sí. Probando, probando, probando. Hola, 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 hola. Hola, hola, probando, 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 probando.
Hola, buenos días. Habla Sergio.
Uno, dos, tres, probando, probando. Hola, hola, ya no hay eco, pero está muy bajito. Solamente cuando haya sector de preguntas vamos a habilitar el audio de acá para que puedan escucharse las preguntas de otras sedes o de los que están afuera. Ahorita no hay eco, he quitado el audio de acá, igual que ayer. No está habilitado. Solamente para el momento las preguntas van a habilitar todo. Sí, 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 probando, probando. Estamos probando sin eco, solamente para las preguntas vamos a poner un 40% de volumen acá. Hola, hola, sí. Sí, 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 sí.
Hola, buenos días.
Sí, solamente la...
Hola, buenos días.
Hola, hola, sí, sí, no hay eco, sí, sí, no hay eco. Para aguanta. ¿Ves? No sabe manejar. No hay presentaciones, van a traer cada uno su presentación. No, no, van a traer recién. Los dos iniciales son virtuales, van a compartir ellos. Recién se va a conectar, recién no hay 40, una vez terminando el evento de inauguración. Hola, estoy aquí. Hola, hola. Ya. ¿Qué efecto? Ya, mira, todavía.
Yo supo decía que no estás. Te llamo en mis horas tristes de pena y soledad. Te llamo en mis horas tristes de pena y soledad. Ya, 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 sí, ya.
Ya, todo bien, todo bien, todo bien. Sí, yo,
Ya,
sí, yo.
bueno,
Excelente. Es que nos hacen la prueba. ¿Dónde lo tengo? Aquí está en cabina. Excelente. Está en cabina. Ah, sí, ok. Bueno, en unos minutos iniciaremos con el acto de inauguración de la quinta conferencia sudamericana en comunicación por luz visible, SACVLC 2025 y Triple E Univalle. Se lo solicita gentilmente coloquen sus dispositivos móviles en modo silencio. Muchas gracias.
Hola, hola. Hola. Bueno,
Aló, 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 probando, aló, aló, ayer, aló, aló,
buenos días. Daremos inicio al acto de inauguración, por favor. Les pido que tomen asiento. Ok. En unos 4 minutos ya empezaremos. Gracias por esperar. Se inició la acto de inauguración oficial. Iniciando el evento, se desea indicar que la Universidad Privada de la Unión es coorganizadora y sede de la quinta conferencia sudamericana en comunicación por los visibles, SACVLC 2025, junto al Instituto de Ingenieros Eléctricos y Electrónicos de Lima y a llevarse a cabo los días 22, 23, 24 de julio del presente año. Este evento científico internacional está enfocado en mostrar avances en tecnologías de comunicación por los visibles, VLC, y sus aplicaciones en sistemas de comunicación y procesamiento de señales, comunicaciones cuánticas, redes de comunicaciones inalámbricas y móviles, tecnologías biomédicas, ambientes inteligentes, redes de comunicación 5G, de 5G, 6G, además de otros tópicos en sistemas de electrónica integrados, sistemas de control e inteligencia artificial. La conferencia reúne investigadores académicos, profesionales y estudiantes de todo el mundo que trabajan en este campo, con el objetivo de exponer, colaborar y discutir sobre sus últimos avances, desarrollos a través de charlas magistrales, invitados especiales y presentaciones técnicas. Damos la bienvenida. Iniciamos la quinta conferencia sudamericana en comunicación por voz visible SACVLC 2025. Saludamos e invitamos especialmente a subir a la testera a las siguientes autoridades, por favor, por el lado izquierdo del auditorio. Ingeniero máster en Ciencias, Franklin Néstor Rada, vicerrector de la Universidad del Valle, sede de La Paz. Pase, por favor. Un aplauso. Le invitamos a continuación al profesor Ismael Soto Gómez de la Universidad de Santiago de Chile, co-chair, copresidente del Comité Sudamericano Organizativo de la conferencia. También invitamos al ingeniero Fabio Gutiérrez, Section Chair, presidente de la sección de AAA de Bolivia. Finalmente, invitamos al ingeniero Chair, presidente local, Comité Ejecutivo Triple, sección de Bolivia, y vicepresidente del Consejo Andino Triple. También saludamos a los invitados inscritos en esta conferencia, para que tenemos profesores, docentes y alumnos de las universidades y público en general. Como antecedentes, nos gustaría informar que la primera edición de la conferencia se realizó en el año 2017. Sudamericana en Comunicación por los visibles SACVLC 2025 y PPE Univalle. Continuando con esta agenda, escucharemos las palabras de acá del ingeniero de Ciencias Franklin Néstor Rada, vicerrector de la Universidad del Valle, sede de La Paz. Adelante, por favor.
Muy buenos días a todos y a todas los asistentes. Bueno, hacer una pequeña aclaración. Yo soy el director de investigación de Univalle, soy el doctor Rodríguez. Estoy en representación de nuestra máxima autoridad, que es el ingeniero Néstor Franklin Rada. Por motivos de salud, él no está presente y lo estamos representando. ¿Ok? Entonces, permítanme, por favor, saludar y dar la más cordial bienvenida al doctor Ismael Soto Gómez, experto en comunicaciones y ópticas inalámbricas y amplia trayectoria en la Academia de Investigación Internacional. Al profesor Fael Gutiérrez, que es el presidente de la IEEE, al profesor Elías Choque Maidana, que es parte del miembro del comité ejecutivo de la IEEE, de la sección Bolivia, que es vicepresidente del Consejo Andino de la IEEE, y a todos los asistentes que nos acompañan en la modalidad virtual. Bueno, tengan ustedes todos muy buenos días. Como director de investigación de la Universidad Privada del Valle, les doy la más cordial bienvenida a esta quinta conferencia sudamericana sobre la comunicación de luz visible. Sin duda alguna, este evento es tan importante que marca un hito académico y una gran oportunidad para los estudiantes, para los docentes y lógicamente, para los investigadores. ya que aborda tecnologías que están marcando el futuro de en telecomunicaciones y en ingeniería, medicina y automatización. Nuestra universidad, como sede organizadora de este evento, gracias a más de 20 años de compromiso con una educación innovadora y de alta calidad, se siente muy honrada en tener la actuación y la ejecución de este evento. Eventos como este nos permiten fortalecer la conexión entre la teoría y la práctica y motivan a nuestros estudiantes a liderar el cambio tecnológico y científico en cada región. En ese sentido, agradezco nuevamente la presencia de todos los invitados, de todos los concurrentes que nos acompañan, no solamente desde de Bolivia, sino también a todos los participantes que están acá, que han llegado en estos últimos días. Les doy la más cordial bienvenida a nombre de nuestra máxima autoridad y que este evento sea de gran beneficio para todos nosotros, no solamente para los estudiantes, que nos permita poder crear, fortalecer las alianzas que estamos realizando con los organizadores y poder que sea el primer paso para poder desarrollar muchas más investigaciones y eventos de este tipo. Muchísimas gracias.
Agradecemos sus palabras a nombre del señor vicerrector. Continuando con el programa, invitamos a escuchar las palabras a cargo del profesor Ismael Soto Gómez de la Universidad de Chile, cochair y del comité organizador de la conferencia. Por favor, pase. Un aplauso, por favor.
Good morning. I will do my little speech in English because this meeting is transmitting to internet to England and Europe because we are only the South American branch of a big team that come from Europe. I would like also give my regards to the people that come from England to present some works in this conference. Most of our presentation will be in English, and we will do with simultaneous translation. Yes, but because this conference is broadcasting to Europe, and the people is listening and see on the right. So in behalf of the International South American Organizing Committee, I would like to express my deep gratitude to the people of Bolivia, in particular to my colleague Zavala, who did the contact with his friends in Bolivia, and in special Jaime Rodriguez, the director of the research university, also the representative of the IEEE for this warm reception and the possibility to expand the South American colloquium to be performed in different countries. Maybe you know that we've been doing this before in Brazil, and most of the time Santiago, but now it's time to go up and try to cover all the continent. And well, I have prepared a little presentation on the topic that we will present, but you did already for me, so I will say thank you for the reception and all of you. Thank you very much.
Muy amable, gracias por sus palabras. Eh, a continuación, invitamos a escuchar las palabras a cargo del ingeniero Fael Gutiérrez, sección chair, presidente de sección y Triple Bolivia. Adelante, por favor.
Muy buenos días a todos, distinguidos invitados internacionales, autoridades de la Universidad Privada del Valle, expositores, colegas, estudiantes y miembros del IEEE. Es un verdadero honor darles la más cordial bienvenida al Congreso SACVLC, un espacio que reúne a mentes brillantes, jóvenes talentosos e investigadores comprometidos con el desarrollo científico y tecnológico de nuestra región. Quiero expresar mi profundo agradecimiento a la Universidad Privada del Valle por abrirnos las puertas de su casa de estudios y brindarnos sus instalaciones para este importante evento. Gracias a su apoyo, hoy podemos compartir conocimiento, experiencias e inspiración. Como presidente de la sección IEEE Bolivia, me gustaría compartir brevemente los objetivos que nos guían. Nuestro objetivo es promover la educación, la investigación y la innovación tecnológica, conectando estudiantes, profesionales y académicos para generar impacto en nuestras comunidades. Creemos que la educación es la herramienta más poderosa para transformar sociedades y por ello trabajamos para ofrecer oportunidades de aprendizaje continuo, actualización profesional y participación activa de los jóvenes en la ciencia y la investigación. Eventos como el SACVLC son una muestra concreta de este compromiso. Aquí compartimos resultados de investigación, experiencias profesionales y visiones de futuro. Cada presentación y cada conversación representan una oportunidad de crecimiento para todos. Asimismo, buscamos fortalecer la colaboración internacional. La presencia de invitados y expositores de distintos países nos recuerdan que la ciencia no tiene fronteras y que el conocimiento se construye mejor cuando lo hacemos juntos. Bolivia se siente honrada de recibirlos y de ser parte de este intercambio académico que enriquece a nuestra comunidad y a la región latinoamericana. Entre nuestros objetivos también está impulsar la participación estudiantil, apoyar los capítulos técnicos y fomentar espacios de mentoría y liderazgo. Queremos inspirar a los jóvenes ingenieros y científicos a creer que desde Bolivia también se puede contribuir al avance global de la tecnología, la sostenibilidad y la innovación. Agradezco sinceramente al presidente del comité organizador, Elías Choque, a todos los organizadores locales e internacionales y a todos los voluntarios que hicieron posible este evento. Y por supuesto a ustedes, los participantes, por su presencia, entusiasmo y dedicación. Los invito a aprovechar al máximo estos días. Participen, pregunten, compartan ideas y formen redes. El verdadero valor de este espacio está en las conexiones que generamos y en el conocimiento que construimos juntos. Sean todos muy bienvenidos a Bolivia y al Congreso SACVLC. Que este encuentro sea una fuente de inspiración y un paso más hacia una región más educada, innovadora y unida. Muchas gracias.
Agradecemos las palabras del ingeniero Fael Gutiérrez. Muchas gracias. A continuación, invitamos a escuchar las palabras a cargo del ingeniero Elías Choque Maidano, local chair, presidente local, comité ejecutivo IEEE sección Bolivia y vicepresidente del Consejo Andino IEEE. Pase, por favor, ingeniero. Un aplauso.
A ver, primeramente, muy buenos días a todos, a nuestros visitantes externos que llegaron de varias latitudes del mundo. Tenemos presencia desde Argentina, de Chile, desde Reino Unido, de Brasil, ponentes de Cuba. Primeramente, antes quisiera dar un saludo al doctor Jaime Rodríguez, que está en representación del rector, a Fael Gutiérrez, que es el presidente de la IEEE sección Bolivia, y también a nuestra vicepresidenta de IEEE Bolivia, Cecilia, una amiga de tantos años en el voluntariado IEEE. En nombre del comité organizador local y en nombre de IEEE sección Bolivia, es un verdadero honor darles la bienvenida al quinto Congreso Sudamericano de Comunicaciones Visibles, SACVLC. Hoy no solo inauguramos este congreso, sino una página en nuestra historia científica como Bolivia y universidad. Es un hito significativo puesto que en Bolivia no se realizan eventos con tal frecuencia y de esta envergadura. Desde esta casa de estudios que es Univalle, eh, se reúnen investigadores, profesionales, estudiantes, docentes de varias latitudes para compartir conocimiento, ciencia e innovación. Durante estos 3 días de congreso, muchos de los ponentes presentarán y defenderán sus papers, los resultados de días, meses o hasta años de investigación. Ellos nos contarán la historia de cómo se ha construido su paper de la ciencia. Claro, esas historias contadas, pero en lenguaje científico. Estamos en un espacio donde convergen las ideas más recientes en comunicaciones ópticas, cuánticas, inteligencia artificial, sistemas embebidos, electrónica avanzada, entre otras áreas, definiendo los límites del futuro de la ingeniería y la tecnología moderna. Que hacemos aquí por inspirar soluciones reales a los desafíos que tenemos como sociedad. Invito a cada uno de ustedes, ya sea investigadores, estudiantes, docentes, profesionales, a participar de las sesiones para conectar, debatir. Cada uno también quiero pedir especial a los estudiantes, eh, aprovechen esta oportunidad. Es una oportunidad única para aprender y dialogar con investigadores de talla mundial. Tomen cada charla, cada conversación y cada demostración durante estos 3 días como una fuente inspiradora académica, que detrás de los expertos que hoy nos visitan, seguramente hace tiempo, estudiante como ustedes, pero curioso y que quería ir un poco más allá. Que este encuentro para ustedes sea una chispa que encienda nuevas vocaciones, quizás científicas, académicas, de nuevos proyectos y fomentar tal vez y plantearse nuevas metas profesionales. Las oportunidades que pueden conseguir con los talentos que necesitan son grandes. Aprovechenlas, no se repiten cada vez. Que este congreso es para nuevas colaboraciones, nuevas ideas, nuevos sueños científicos. A todos les deseo un excelente congreso. Bienvenidos al SACVLC 25. Gracias. Agradecemos las palabras del ingeniero Choque Molina. Les pido un momento, por favor, que tengan estimadas autoridades. Muchas gracias. Esa sería la presentación por ahora. Un aplauso, por favor, a las autoridades. Gracias. Con conciencia, por favor. Entonces, lista en el escenario.
Se tienen varias típica de cacho quizá que recibimos con un fuerte aplauso, por favor.
Yo supo que estás, te llamo en mis horas tristes, pena y soledad, te llamo en mis horas tristes, de pena y soledad. Añoro, añoro tus labios todo el fulgor. No podré olvidar labios con no podré olvidar lo sexy de tu boca, que no puedo tocar, no menos el corazón, deja de olvidar, cuando el corazón, deja de olvidar. Deja de palpitar. Yo sufro de ella, mujer cosa, llamo en mis horas tristes, de pena y soledad, te llamo en mis horas tristes, de pena y soledad. Añoro, añoro, tus labios todo el cuerpo. No podré olvidar tus labios todo el cuerpo. No podré olvidar la ausencia de que no puedo soportar. No menos el corazón deja de palpitar. Cuando menos el corazón deja de palpitar. Mira, 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 mira. Cuando menos el corazón deja de palpitar.
Fuerte aplauso, por favor. Agradecemos nuevamente a la Folclórico de Nueva York. Muchas gracias. Pues, nuevamente que las autoridades pasen al escenario para una foto de inauguración. Serían tan amables, por favor. Un aplauso, por favor. Muchas gracias, muchas gracias. Gracias, muchas gracias. Sí, en confianza. Vamos. Sí, hay una parte de adelante, lado derecho e izquierdo del letrero. Sí, 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 es una excelente idea. Gracias, muchas gracias, chicos. Ah, tu chamarra. Los más altos en la fila de atrás, por favor. Muchas gracias a todos. Sí, sí, sí. En 2 minutos iniciamos con la presentación. El doctor Muhammad Ayas. Ya. Recordemos que las presentaciones magistrales se ven en inglés y las preguntas pueden ser elaboradas también en español para traducirlas al inglés. Por tanto, damos por inicio a la quinta conferencia sobre el mercado de comunicación por luz visible, SACVLC 2025 y tipo de Bolivia. Agradecemos a todos. Vamos a dar inicio con la primera presentación magistral. Start with the first keynote. A cargo del doctor doctor Ayes. Va a comenzar la producción de su biografía en español y luego en inglés. Doctor Ayes, que realizó su maestría en Ingeniería Optoelectrónica y de Comunicaciones de la Universidad de Northumbria, Reino Unido, en 2009. También ha sido becario de la Universidad de Northumbria para su doctorado. Su título de doctorado en 2013 en la misma Universidad de Northumbria, Reino Unido, en Comunicaciones Ópticas de Espacio Libre, FSO. También trabajó como investigador en comunicación luz visible. En la Universidad de 2013 a 2015. Actualmente trabaja como profesor asociado y líder internacional del Departamento de Ingeniería de la Universidad Metropolitana de Manchester, Reino Unido. Es el jefe del laboratorio de comunicación láser y óptica, donde una investigación aplicada en comunicación inalámbrica óptica, sistemas integrados, IoT, redes de comunicación 6G, procesamiento de señales digitales y diseño de sensores inteligentes. Su trabajo se centra en el posicionamiento de interiores mediante luz visible, VLP, una tecnología promotora en el contexto de la industria 4.0 y la creciente demanda de localización y guiado personalizado. En esta charla presentará los avances y desafíos recientes de los sistemas VLP, destacando su relevancia para aplicaciones prácticas y tecnológicas emergentes. Let's welcome to Dr. Mohammed Bajas, who received his Master in Science in Optoelectronics and Communication Engineering from Northumbria University, UK, 2009. He has also been awarded Northumbria University studentship to pursue his PhD. He was awarded his PhD degree in 2013 at the same Northumbria University, UK, where his research work in free space optical FSO communications. He also worked as a research fellow in visible light communication LIFI at University of Edinburgh, UK, between 2013 and 2015. Currently, he is working as a reader associate professor and international leader in the Department of Engineering at Manchester Metropolitan University, UK. He's head of the Laser and Optical Communication Laboratory, where he leads applied research in optical wireless communication, embedded systems, IoT, 6G communication, network, digital signal processing, and smart sensor design. His work focuses on visible light indoor positioning, VLP, a promising technology in the context of Industry 4.0 and the growing demand for personalized localization guidance using mobile devices and wearables. In his talk, he will present recent advances and challenges in 3D VLP systems, highlighting their relevance to practical applications and emerging technologies. Dr. Mohammed, you have the word, please. Thank you very much.
Hi, Muhammad. Can you hear us?
Doctor, can you hear us?
Yeah. Just let me know if my sound is okay in the room, yeah?
I can hear you now.
Excellent. Okay, that's fine then, yeah. Just let me know whenever. Okay. Hi, everyone. Thanks very much for inviting me to this conference. My name is Dr. Muhammad Aijaz. I'm Associate Professor and I'm Head of Lasers and Optics Communication Lab at the Department of Engineering, Faculty of Science and Engineering here in Manchester. I hope you can hear me all right, yeah, everyone? Yeah, all? Can you hear me, yeah?
Yes, no problem.
Okay, excellent. So I will start really, again, appreciation. Thanks very much to the steering committee, particularly Professor Gassamli, Professor Ismail, and also the local committee, Professor Elias, for invitation. And I hope that this conference will be again a very successful event as last year in Santiago. So I'm going to talk about in this next 30 to 35 minutes on some of my research here in Manchester. So I chosen a topic called visible light positioning. So I will be talking about on research and development. We will be looking at some of what we're doing here in Dalton Building at Manchester Metropolitan University. And these are some of the contents which I'm going to cover. So as I said, I'm going to highlight some of my research just in order that maybe there are some young researchers listening me, there are senior researchers listening me, and a wider community from the South America. So I would be looking for research collaborations in future. So I will highlight some of my research here in Laser and Optics Communication Lab. I'm currently sitting in a lab, and then I will come to my topic, which is visible light positioning. So I will share with you some of my latest research in visible light positioning, some of the challenges which we're trying to tackle and advances in this area, and then I will conclude my presentation. So just to give you a brief introduction of my university, we are based in Manchester. Many of colleagues, Ismail, Caesar, and many other colleagues visited me time by time. And this is our campus in Manchester. You can see the aerial view of the city. We have 4 faculties, and we are based in the Faculty of Science and Engineering at the right top corners in a brand new building, which you maybe saw in my first slide, which is Dalton Building. And we have a range of research which basically from the science and engineering background to business and education and so on. So our faculty is our university is quite big. If you walk from the right side to the left side, it's about 20 to 25 minutes walk. So this is our university with some of the pictures of Manchester City. So I am based in the Laser and Optics Communication Lab. I am leading and heading this lab, and we are looking into optical wireless communication, visible light positioning, free space optics. We also done a lot of work in signal processing, modulation schemes, and we are now looking for hybrid system and terahertz frequency spectral bands as well. With the new smart technologies, such as smart connectivities, we are looking sensor design and also the machine learning and artificial intelligence implementation in communication and connectivity. Within this lab, for till now, I secured about close to £1 million funding in the last 4 or 5 years, and I've worked with a number of companies. You can see at the bottom left side, some of the companies, 2-meter Arctic case, polymer label, and on the right side, you can see some of the pictures of the lab where we are doing sort of multidisciplinary kind of research. These are some of the pictures which some of my PhD students and MSc students experimental test beds, just to show you. And you're really welcome to come in the lab. We are now thinking, we work really towards the commercialization and prototyping. So we are basically looking on low cost, energy efficient, green, Li-Fi complementary sort of links for to complement the radio frequency, where you may witness a lot of challenges. So we are currently looking on prototyping and so on. As I said, I think I've already given a little background, but these are some of my funded projects from Innovate UK, from UK Research and Innovation Council. And I work very closely with the local and national industry in a sort of multidisciplinary applied and commercial research as well. This slide, I just want to give you some background on my research collaborations. You can see that I have very high quality collaborations with the South American universities, including University of Chile. Cesar is my main contact, and the team from there, University of Santiago, Professor Ismail, and a number of other colleagues. Then we have other, collaboration with Chilean partners and from Ecuador as well. You can see some of the universities. With that, I have also a lot of research collaborations in UK and across the globe. I just want to give you a brief introduction on my current research beyond visible light positioning. I know you people, a lot of people in the audience know about visible light communications, so I'm not going to spend a lot of time here, but essentially we use visible spectrum for visible light communication, and there are a lot of benefits, but I think what we're really looking on the communication 5G and 6G standards, and we want to see that how we can enhance and these sort of standards and also contribute in those standards using the visible light as indoor communication. We're looking really for high speed data rates using the visible light or Wi-Fi networks, and also the 6G networks. You know that the demand for that is higher data rates, ultra reliable, low latency, and also massive connectivity, where we are looking at large connectivities at very dense populated areas. And also these 6G networks, we are looking at these should be more greener than intelligent. So these sort of metrics, we are looking for 6G network, and we think that visible light communication can sort of contribute into these metrics of 6G. You people know about the Wi-Fi networks. On the right side, you can see some of the practical example how we kind of envision these networks in future and in the 6G indoor implementation. But there are a number of challenges in the Wi-Fi networks or Wi-Fi or visible light communication. One of the challenges is the front ends are particularly the light fixtures, the LED-based light fixtures. The LEDs itself are slow. Usually the bandwidth of these commercially available the illumination devices, particularly light bulbs based on LEDs, they give us a bandwidth about from 5 to 10 megahertz, or maybe up to 10 to 20 megahertz. Yeah, and this is really a challenge, because when we try to modulate using on-off-key modulation scheme, the slope of these, these modulation data is limited because of that, and we're really not close to the real sort of an infinite slope. So therefore, that really causes a sort of a problem in order to achieve higher data rates or spectral efficiency because of these low devices. We can essentially try to tackle this problem with the multi-carrier modulation schemes, and many of you may have implemented that. It's really very well working. And one of the RTE standard as well. Essentially, if we use FDM, we can increase the spectral efficiency with a log of 2. And this modulation scheme is easy to implement as well, because we just need a single tap equalizer. And we can also more efficiently use it with adaptive bit and energy loading, which means that if our communication Wi-Fi channel is not very flat, or the power of the channel is not sort of constant, is varying with the channel constraints, then we can utilize that channel or bandwidth more efficiently. So which means that we can back more sort of bits, where we have a more channel sort of energy. So we can essentially use OFDM to increase the spectral efficiency. And I have also worked on the spatial modulation back in Edinburgh University, where we also try to increase the spectral efficiency by using multi-input and multi-output techniques, MIMO techniques. And one of the techniques is called spatial modulation, where we can use the indexes of the antennas or position of the LEDs to code data with the general sort of modulation scheme, such as OFDM. So essentially, you can increase your spectral efficiency with lot of number of the LED you use plus the spectral efficiency you getting from the OFDM or any other modulation scheme. So you can essentially increase further spectral efficiency, but it's still a factor of logarithm, log of 2. So essentially we are increasing spectral efficiency by utilizing these higher order MIMO techniques from OFDM and onwards. And we have done some experiments where we have taken the LEDs, which are more smaller in size, which mean these are a little bit faster, a lot of faster the modulation scheme with a faster data bandwidth or higher bandwidth. So we've taken a bandwidth up to up to devices up to 250 megahertz, which are essentially a large bandwidth when you compare with off-the-shelf devices like with 10 to 20 megahertz, that sort of devices. So we use these devices in order to see how much data we can harness out of these devices using spatial modulation. And you can see from this study where we try to implement experimentally the OFDM using a single input and a single output with the spatial modulation, which is a MIMO technique. And we are able to enhance our...
Excuse me, Muhammad.
Per second. So we try to increase the spectral efficiency in this study was when we've been increasing the semi-angle of the LED, which means when we try to beam.
Sorry. Salió de la comunicación su problema técnico. Otro lado. Mientras conseguimos la recuperación del doctor Hamad, recordemos que habrá un coffee break a las 11 y después 3 presentaciones, 3 ponencias seguidas. Hacer sus preguntas en español y las traduciremos al inglés. y traducir la respuesta del inglés al español. Y claro, mejor si preguntan en inglés, por supuesto.
Okay, good. Okay, glad to get that. Okay, let me reshare my slides again. Yeah. Okay. Okay. Could you be able to see slides? Yeah.
Yes, we can.
Okay. Excellent. Excellent. I do apologize for. Yeah, I do apologize, guys. It maybe something happened which I'm not aware of, and I don't think so. We lost much. Right? Yeah. So are you guys able to hear me? Yeah. Okay. Okay. So yeah. So okay. Thanks everybody. Yeah. So I just really recap on where I've been. So I've been trying to explain on spatial modulation, where we essentially can increase the spectral efficiency. And we do that because we have a limited bandwidth of the front ends, particularly our transmitters. And we have implemented that experimentally, and our aim was to achieve 1 gigabit per second, and we've been able to demonstrate that at narrow beams. However, when we open the beams, I've been trying to say that the data rates drop such as it drops almost exponentially, or so that is fine. This is expected because our the devices were low power, but if we want to make that a constant and 1 gigabit per second are at all LED semi-angles, we can essentially bring more high power LEDs, and we can be able to achieve that. Okay, so let me move further. We have done some sort of experimental work recently. I presented that in IEEE CS and DSP last year, and we are looking on more greener Li-Fi transceivers, where we think that the receiver should be able to harvest energy with the data transmission, and then we can use that energy to power our transmitter, or at least transceivers, or at least one of them, like transmitter, So in this experimental work, what we have done, we have used. Should I need to unmute here? Raul, is that okay? Yeah,
It's fine. Please continue.
it's fine. Okay. So in this experimental work, what we have done, we have taken a golden trigger commercial LED, we modulate with on-off keying and on-off keying modulation scheme, and then we use the solar cell as the receiver. And the idea was to use a combination of solar cell to harvest energy, and also to provide connectivity to at least low data rate IoT sort of applications. And in this study, we've been able to harness the energy, and as well as we've been able to power the transmitter. And this is a kind of some of the first experiments where we're trying to make the system more self-powered. On the right side, you can see some of the experimental testbed which we used, including the Keysight signal generators and oscilloscopes, and the experimental testbed in the bottom right side on the green surface. You can see some of the LEDs, PCBs, and also the solar cells. So what we did in this test, we have implemented the bandwidth analysis. We looked into the combination of, we used a combination of solar cell at the receiver, and we then looked into combinations like 2x2, 4x4 in series and parallel. So we wanted to sort of, we wanted to see sort of which combination if we connect the solar cells in a series, give us a better results, or in a parallel. And by theory, we expect that the series should give us more sort of the energy harvest and also the bandwidth, because the voltage is added in that. So you can see, first of all, what we did, we took the we took the system and then we tried to analyze its bandwidth, and we concluded that the series in 4x4 gives us a better bandwidth, and we achieve maximum bandwidth with this experimental test bed up to 71 kilohertz. And then we implemented energy harvesting, and we again saw that 4x4 combination of solar cells in series, when we connect them in a series, give us a better energy harvest up to 80 milliwatt. And then we also able to successfully transmit about 50 kilobit per second data rate. But the problem in here, our system was using LED here, and this was limiting our link range. So the distance between the LED and the solar cell. This means we were not able to achieve a very good link distance. And to cope this problem, we recently did some work with Professor Caesar from University of Chile, where we modified the transmitter with a laser, and then we have the receiver which is based on a solar cell, and this is our receiver in the middle. It's a little bit better version of what we have done before, but we used laser instead of LED at the transmitter end, and we'll be able to achieve the higher distances up to 7 meters, which is really, really good. So this concludes that we'll be able to achieve higher distance or longer ranges in the self-powered or simultaneously light and information power transmission systems. But we need to change our front ends to lasers, and hence we can be able to achieve higher distance. And you can see that is demonstrated in our BER versus distance curve as well. So in this experimental test bed, we use polycrystalline silicon-based solar cells with modulation scheme on-off keying, and we've been able to achieve 25 kilobit per second, which I think is a sort of good data rate for IoT applications. Right, so this sort of, the experimental and research work we are doing towards implementing Li-Fi, particularly signal processing, and also we're looking on the spectral efficiency signal processing, and also the self-powered and split sort of systems, where we try to use these systems for the simultaneous power and information transfer. And the next of the presentation I'm going to talk about on visible light positioning, where we are trying to implement different algorithms to use in the localization for indoor industrial applications. And we are looking at that because we are looking for Industry 5.0, and we are looking for more autonomous sort of industry where we have a less human interaction. And one of the challenge in sort of these industrial or application, these are indoor, and indoor radio frequency system doesn't really work very well because of the blockage of signals. So we think that the light can be used to localize, or can be used for the aerial vehicles indoor, such as drones and so on. You can also achieve higher sort of localization, precise localization, or higher sort of quality of positioning or localization with the by using visible light. The reason is because we get more signal to noise ratio, or more high powers with visible light rather than radio frequency. So ideally, this work is really focusing on the indoor industrial applications, and indoor industrial application, particularly where we have the drones working, where we have the robots working indoor. And as I said before, that we don't want that the human interaction once it's not really allowed in those sort of high risk applications, or maybe is very limited. So we wanted to use that technology to localize, or for different positioning algorithm for indoor applications using the light. So In this study, what we have done, we have taken a very large sort of warehouse. The dimensions of those could be from 0 to 25 meter and 0 to 15. And these are very large rooms or indoor spaces. And we implemented our visible light positioning, as I said before, on industrial application. Therefore, we try to sort of simulate a similar real world case here. And we also taken on the right side, you can see we have taken a number of LEDs which are represented here with the stars on the figure on the top, figure A. And we then also propose a sort of a path for the drones where we want the drones to follow, and we will use algorithms based on the visible light positioning, and then we try to localize our drone and check its performance in terms of the positioning errors and other, signal to noise ratio or receive power in those sort of metrics. Before we did this work, we also tried to make sure since we're taking very large spaces, is a unique spaces because the indoor spaces for our living are very small comparing to the industrial applications. And there could be very different settings as well, particularly the hardware, inside those spaces or the commercial, the settings and so on. And we try to we try to see if we are able to provide the right level of illumination. So therefore, we use some sort of simulation using a Dilex to see that the system model we are adopting is basically realistic. And in this case, you can see that we have chosen 15 high power LEDs, which or light fixture, which with the optical power up to 80 watts and so on. And we then able to simulate our system. And you can see that we have a very good coverage, the yellow parts. And however, near the walls, we have some problems where we have more sort of bluish, sort of results. But largely, we first checked that we are getting 282 lux, which is the European standard, up to a desk height of about 0.8 meters. After that, when we are sure that, okay, we are able to eliminate a large room, then we can, look into the implementation phase. So as I said before, we used high power LEDs up to 80 watt, and we choose an awesome second generation compact light fixtures. And we use a very traditional Li-Fi or visible light communication channel. You can see in this figure on the left side where the channel is a function of the few angles, alpha and beta, and it's a function of the area of the receiver and also the Lombardian order of the source. So we also consider the bandwidth of these devices is about up to 10 megahertz. So we need a trilateration algorithm to work with, and the algorithm we choose is called Cayley-Menger determinant. Based on that, we try to basically implement the trilateration algorithm, which is shown in the figure B. And to work this algorithm, we need at least 3 light sources or light fixtures. And we try to estimate the distances between the source P1, P2, P3, which basically representing light fixtures here. And when we know the distance between these sources, then we're able to implement our trilateration algorithm. We have used, as I said before, a standard visible light positioning model. And the standard light positioning model is based on the DC channel gain. As I said before, it's a function of the Lombardian order and the sum of the angles between the transmitter and receiver, and also the area of the receiver and the distance between them. So from there, we can be able to calculate the distance vector, which is a function of the power received. In the denominator, you can see the PRI, which is a function of, so your distance between the transmitter and the drone is a function of received power, essentially. So we try to calculate distance based on the received power, which is this is why we're saying that this algorithm is based on received signal strength. And then we implemented some sort of other cases where we can also try to include the tilt between the transmitter and the receiver. And this happens that because we are considering here the drone applications, when the drone moves, it tilts a little bit towards forward positioning, and this is causing a little bit sort of a line of sight case, which means that it can impact our received power as a result of the received signal to noise ratio and also the performance metrics as well. After our VLP system model, we also plan to test this. So for that, we also established a visible light positioning test bed. And this test bed has the similar sort of LEDs on the ceiling, and we used microcontroller units, in this case Adafruit, and we use the FDM in this case, and then we used the signal transmitted through LEDs and received on the receiver, and then we have done post processing of the signal to validate our positioning algorithm. So this is our experimental test bed, which we established with the University of Ghent with Professor David Platts, and we have used that to estimate our positioning algorithms. So when we done our system model, we performed simulations, and we used because we need to estimate the height of the receiver as well, which is sort of a three-dimensional positioning. For that, we implemented cost function, and we've been trying to estimate the height using cost function, and we've been trying to minimize to 0. And you can see that we have implemented cost function with Kalimanger and linear least square as algorithm as well. We compared these two algorithms for positioning. Linear least square algorithm is one of the very general one which everyone uses really for trilateration algorithms. And we then also included both algorithms with tilt, and you can see that when there is no tilt, the cost function is minimizing to almost 0, and estimating that the receiver position is about 2 meter height. But when there is a sort of tilt, then you can see that it's now very sort of with a very big curve. It's not minimizing to 0. It's a little bit more sort of flat here, and this is because the tilt causes reduces the power received, and as a result of that, we have this issue. However, when we implemented this algorithm on our positioning algorithm for 3D positioning, and you can see that we've been able to achieve a very, very small positioning errors, which mean our algorithms were very, very precise or / accurate, And you can see that the positioning of estimation with CMD is a little bit better than the LLS algorithm. And we implemented that, and this is a sort of very ideal case where we have just the simulations with a very, sort of ideal noises. So therefore, you can see that the positioning is very accurate, which I think is fine because these are simulations. But we also tested with the experimental results. You can see here in this case. And here we estimated the same algorithms with simulation and you compared with the experimental results, the simulation results, and you can see here that the positioning errors when we implemented on the hardware, which I showed you in the previous slide, the positioning errors are increases up to 35 centimeter. And this is expected because this is sort of non-ideal case where we have noises from the hardware and so on, and also the received signal, is not as ideal as we used in the simulation. So in the simulation, you can still see that the errors are less than about 5 centimeters. But when we increase the maximum errors, but when you increase when we implemented on the hardware, this has increased to 35 centimeters. So this slide just shows that the errors are increased when we implement it on hardware or on experimental test bed. We also looked into the other challenges when the drone moves, the drone tilts, when it moves to the different locations. You can see from this simulation, when the drone is moving, the azimuthal angle is changing. This is because of the tilt, and we have then considered tilts in our simulations, and we tested with the ideal case. And you can see here, we have considered the tilts from 1 degrees to 5 degree. It is like a forward leaning sort of tilt, and you can see the errors been increased up to 1 meter. So we started our simulations with no tilt, and you saw in my previous slide that errors been up to 5 centimeters. Then we implemented on experiments, and then we added tilts. The errors increased to about 1 meter, which is exactly what we expected. Because these are kind of known ideal cases and expected. So basically, we are getting errors, yes. It is increasing, yes, but I think these are still considerably low when we consider, the radio frequency system. So these errors have increased, but I think these are still better than up to 100 meters and so on, which radio frequency based positioning gives us. So I think I agree that the errors are increased, but they are still not that up to the range where radio frequency positioning gives us, which is really very positive. Right, then we also included some other challenges. One of the challenges is when we consider the warehouses as kind of these warehouses where we have industrial settings where there is a smoke, where there is a sort of, a landfill, sort of, the landfill areas are, and they are indoor, and there is some sort of smoke, or maybe just the particles of the different vapors, or maybe there is a mist that can attenuate your the signal power, and as a result we can reduce our signal to noise ratio, which we use to estimate the positioning at the end. So we certainly could have these sort of scenarios where our indoor areas are quite polluted. So we have implemented these, which I'm going to show you later on. But other challenge could be, we have some of the areas where the light signals cannot reach because they are very close to the walls. We have a very good illumination in the center of the room, but close to the ceilings, close to the walls. These are not very well lit. So that's why these areas could have a problem as well. So we have done some simulations considering some of the attenuation. You can see in the figure on the right side, our power received at 15 locations. And in the XY plane we have considered, and we can see that when we have attenuation, the power reduces here, and similarly your signal to noise ratio. And then we implemented on our positioning algorithm, and you can see from this figure that the algorithm is losing its precision when we have some sort of attenuation, because these algorithms work on the received signal strength, and as a result, the algorithm doesn't perform as we expect, and the errors increases. To solve this problem, we implemented machine learning algorithms, and Rahul is here right now. We done that work in the last SACVLC, and we tried to implement the AI/machine learning algorithms, and in this case we use the neural network algorithm, and you can see that some of the results here. We first trained, we basically took the simulation data of the errors up to millions of samples. We tried to train that data, and based on that training, we have implemented, the algorithm here. And after the machine learning neural network algorithm, where we showed in this study that with the machine learning algorithm, we can improve our errors from 21.99 centimeter to about 6 centimeter. On the left side, you can see that there are green sort of samples. These samples are with noise and with attenuation. And these samples shows that the expected algorithm, which needs to localize the drone, is it kind of have a higher errors. And when we implemented the machine learning algorithm, the errors decreased. Hi, Rahul.
Yes, sir.
Hi, Rahul.
We are you're on the Zoom, I'm sorry.
Exactly. I wanted to just really summarize. I know that I'm up to the time, about 40 minutes. I apologize. There were some issues in the connectivity. But in this talk, I just wanted to give some of my research, which I'm doing here at Manchester Metropolitan University. And I'm looking on areas like health, transport, or smart infrastructure. And also, we are looking on visible light positioning. We try to look on some of the challenges which I just highlighted. I know I haven't compared my research with other authors because I don't want to. I just wanted to show which I am doing, and I want your people involvement so that I can improve my research further, and I can contribute into wider visible light or optical wireless communication research. Once again, thank you very much to the steering committee, to the local committee, and I wish you all for a wonderful next 2 to 3 days. And I hope people will enjoy it. I hope it would be a successful conference. And I do apologize, I couldn't really make it. I would like to make it, but unfortunately, I couldn't make it. So I am certainly missing this conference. So that's it really, Rahul and everybody.
Thank you, Dr. Mohammed. Yeah, we are over time, but maybe we can have one question.
Hello?
I have a question, Doctor. I know that one of the drawbacks of the visible light communication is the obstacles. In your
Yes.
experiments, what kind of technique do you have in order to tackle these obstacles that might happen? Maybe a distributed estimation with the sensors, or perhaps a different type of algorithm?
Very good question. Honestly, I've been talking to my student, one of my undergrad students, to look into that challenges, and we've been talking about same idea as we have in the millimeter wave intelligent reflected surfaces. So why not we have some sort of intelligent reflected mirrors, you know? So we are looking to use some same sort of ideas which we use in the radio communication. A lot of research is going into the intelligent reflected surfaces, IRS. I think I would say this would be intelligent reflected mirrors. So I think we can use those to direct our signals so that we can mitigate the optical impact. We can also use different relay sort of ideas as well, where we have, the relays in the radio communication. So these sort of ideas could be used to tackle the obstacle.
Oh, okay. Thank you. Thank you very much for the answer.
Ijaz, can you hear me?
Thank you once again to Dr. Mohammed. Un aplauso por favor al Dr. Mohammed. Muchas gracias.
Thank you so much, everyone. Thanks. I'm very happy to see Shani's face, Ottomans, and I know many more are sitting there in the hall, which is not able to be visible here, but really glad to see you all people.
Goodbye, Dr. Mohammed. Thank you. Thank you very much.
Okay, thanks.
Bueno, gracias a todos por la paciencia de los problemas técnicos. Hay un coffee break que ya empezó desde las 11 hasta las 11:15. Por favor, si quisieran pasar a tomar un descanso, a las 11:15 empezamos con con la siguiente ponencia. Gracias.
Hello, can you hear me?
Yes, Zone looks puzzled.
Hello, everybody. Can you hear me?
Yeah,
Yes,
we can hear you.
I said you look puzzled with a wide eye.
It's very
Where are
nice
you?
to see you,
You're not
Fari.
in South America, you?
No, I have no money. If you sent me, I would have,
Oh, you should have asked. Ijaz, that was a very interesting talk.
Thank you, Fari, for appreciations. It's all because of your guidance, Fari.
No. I think it's an interesting work. Well done.
Thank
Well done
you.
that you are still maintaining that experimental verification of yeah, that is the old OCRG. And I can see Osman is also smiling.
So it's very good to see all of you, Fari and Ijaz and Zuna along them.
I can see Ismail somewhere at the front.
Well, you can. I can't really. I think my screen is very small.
I think he's sitting somewhere at the front.
Yeah. Rahul, sorry. You know why I've been not able to hear you people, because they give me a new system where the HP dock. So I connected my system. I think it was mirrored onto my other screen, and that has no speaker.